Lasers are used everywhere, from ordinary households to industrial applications and scientific experiments. And the range of fields in which lasers are applied is expanding rapidly. Until now, however, high-power lasers have been blocked from many applications. Bottlenecks include a large installation footprint, restrictions on usage environment, and the high cost of the equipment and its maintenance. The Impact Sano program recently pursued the challenge of shrinking today's large, high-power pulse lasers to sizes that fit in the palm of the hand. The aim of the challenge was to eliminate these restrictions, to achieve a handheld, high-power pulsed laser that can be used anywhere. The target of the project was to develop a miniaturized laser with similar effect to that of existing pulse lasers, and that could be used in any location or environment as easily as a laser pointer. The expectation is that such a laser can find a wide range of applications, from manufacturing through medicine to advanced research. The technology is based on microchip laser technology, a field in which Japan is a leader. Using this technology, the team boosted output tenfold from conventional levels to 20 millijoules. Microchip lasers feature pulse duration 1 order of magnitude shorter than conventional pulse lasers. This means that output of 20 millijoules delivers the same processing capability as a conventional pulse laser with output of 200 millijoules. A major hurdle stood in the way of this achievement: heat removal from the laser medium. When the laser medium is excited with pumping light, the medium generates a laser beam. Boosting laser output entails shining pumping light of higher energy. This higher energy generates a great deal of heat in the laser medium, raising the temperature of the apparatus. This heat imposes thermal strain and distortion in the medium, leading to reduced output and degraded beam quality. If the apparatus is miniaturized, the heating is made all the more intense. Overcoming this problem required revolutionary new technology. The idea the team discovered is called distributed phase cooling, or DFC. DFC is a structure in which transparent, thermally conductive heat sinks are interposed between the disc-shaped laser media. Joining these different materials is no simple matter. Previous joining methods caused separation and stress at the interface that degraded the efficiency of the laser. To solve this problem, the team developed a world-first joining technology that is perfectly suited to the laser medium, delivering excellent optical properties with rapid heat dissipation. With this breakthrough, the team achieved output of over 20 millijoules, succeeding in its target for the development of a handheld laser. Impact is working with users to create practical applications for the developed technology. One application with strong demand in the medical field consists of compact, easy-to-use equipment for laser treatment of skin conditions. The researchers are already teaming up with engineers at manufacturing companies to develop this application.
すでに開発が終わっているものを我々が応用するだけであればまだシンプルにできたと思うんですけれども、それを少しでも早く市場に出すために本当に開発と並行して我々がこの応用の方に参画させていただいているというのは、新しい製品を世に出していく上では非常に貴重な機会だなと感じております。
In this way, approaches to equipment that incorporate handheld lasers have been moving ahead.
今までは非常に大型な本体のこちらの方に発信機が入ってましたので、治療用のレーザーの光を伝送するためにもですね、これも非常にですね複雑な光学計を用いて、非常に大掛かりなアームを使った多関節のアームを使った形で、光を導行していたんですけれども、もうこの度は発信機がこちらに入りますので、病院の中のどの部屋でも使うことができ、ドクターは病院の中だけにこだわらず、往診によって、患者様の自宅にお伺いし、その場で治療することなども可能になってくると考えております。これは本当に驚くようなことだと思います。
This ultra-compact high-power pulsed laser achieves a maintenance-free optical system, eliminating previous restrictions on installation locations and usage environments. We expect this technology to diffuse to a wide range of other industrial fields.